In this second module of the class, we're going to concern ourselves with some more advanced integration techniques. You're definitely going to want to review the different integration techniques that you had from Calc 1. These are your basic integration rules, such as the product rule, the trigonometric rules, the inverse trig rules, and so forth, along with things like the substitution method. If you're unfamiliar with any of those, take some time to get caught up on those before you get started here. Now, with regards to integration, we know that there's not a product rule like there is with differentiation. So anytime we have a product of two functions, we're not guaranteed that we can integrate them. We are with differentiation, but not necessarily with integration. There is something that we can do when we run into a product of functions, and this is defining the inverse of the product rule. So the product rule being the product rule from differentiation. And what this means is that any function that can be obtained through the use of the product rule of differentiation can be integrated through a process known as integration by parts. So this will work well when you have a product of functions, but it doesn't guarantee that it will work. All right, so let's walk through how this could potentially work. So the product rule, so for instance, if I have a function of the form h of x equals f of x times g of x, so we have the product of two functions, then using the product rule of differentiation, that is, we would get h prime of x is f prime of x times g of x plus g prime of x times f of x. So this is the derivative of the first times the second plus the derivative of the second times the first rule. All right, now if we apply integration to this, so here's what we could come up with. So for instance, if I integrate both sides of this resultant equation, so the integral of h prime of x dx, and set that equal to the integral of f prime of x times g of x plus g prime of x times f of x dx. So all I'm saying is if I have determined the derivative of this function through this process, then reversing and doing the integral of that result is okay. I can do that. Now, what will happen is when I integrate a derivative, then those processes cancel out, and I'm just left with the original function h of x. What happens over here is a little bit different. We can't just say this is necessarily f of x times g of x right away, although we know it ultimately is, but unless we knew where this function came from, we wouldn't be able to just jump right to that conclusion. What we can do, however, is just use some rules of integration and split this up into two separate integrals. So this would be f prime of x times g of x dx plus the integral of g prime of x times f of x dx. But we also know h of x is just the product of these two functions, f of x times g of x. That's just from the original statement of the problem. So that's still equal to everything I have on the right-hand side. So let me just recopy that down. Now, I'm going to rearrange some things. So for instance, if I subtract, I meant for that to be a there, not a highlighter. So if I subtract this integral from both sides, so g prime of x f of x dx, and I subtract it over here. I'm just going to do that because it's a lot to write. And if I subtract f of x times g of x from both sides, all right, so what would happen is I'm moving this term to the right-hand side, and I'm moving this term to the left-hand side. This term would be negative on the left-hand side. If you don't mind, just because I'm kind of out of space here, I'm going to go ahead and distribute this negative across the entire equation and just write this as the integral of g prime of x times f of x dx equals f of x g of x minus f prime of x g of x dx. All right, so everything would have been the negative of what I've written here, but I just divided through everything by a -1 to change the signs. Okay, this is an interesting statement, and there's actually a little bit more that we can do here. We can make it a little bit more familiar. If we were to say, let u be equal to f of x. Okay, so I can just replace this f of x with u, this f of x with u, and this with u prime. Okay, because then, u prime is f prime of x, that is. And likewise, if I let g prime of x be a function v prime, okay, so that this would be here v prime, but g of x then, if I integrate both sides of this, I could say v is equal to just g of x, so that this would be v, and this would be v. So what I end up with is the rule, the integral of u times, so v prime dx, I could actually write as dv. U dv is equal to u times v minus the integral, and I'm doing the same thing here. Instead of u prime dx, I'm just going to write it as du. So v du. This gives me a new type of integral that allows me to get somewhere in actually the process of integration. And all I've really done is just kind of rewritten, the product rule. So that is our rule for integration by parts. So this is a great little formula here, and let's show you through an example how this could work. So we have to discover what the values of these functions u and v are. All right, so in this case, I'm just going to guess at it. What I'm going to do is I'm just going to guess u to be x, and then dv to be e to the x dx. Now notice I didn't choose u and v directly, I chose u and dv, because the first part of this integral is u times dv, so I need something that's the derivative of the function v. And I can get the rest of these parts if I were to, say, take the derivative of u, that would give me du, which in this case would just be 1 times dx. And then if I integrate dv, integrating dv would give me v equals the integral of e to the x dx, which is just e to the x. Now, with that, ultimately what I'm doing here, so again, I'm letting u be x, and e to the x dx is dv. And the remaining part of the formula is that this would be integrated as u times v, which u is still x. V we know as e to the x, and then it's minus the integral of v du. So oftentimes we don't get away from all the integration necessary, but our hope is that this next integral is actually something that we can perform. So let's see what happens. So this would be the integral of v, which is e to the x, and du is just dx. And this is an integral that we can perform. So this would be x e to the x minus e to the x plus c. And that should be the integral of x times e to the x. And you can always check these things if you're unsure. And the check is just to differentiate what you have. So x e to the x minus e to the x plus c. And if I differentiate the first term, I would need to use the product rule on it. So that first term would differentiate as the derivative of the first, so the derivative of x is 1, times the second, plus the first times the derivative of the second, and then that's the derivative of this first term. The derivative of the second term is just minus e to the x. The derivative of a constant c is 0, so this is what we have so far. And if you'll notice, I've got a negative e to the x and a positive e to the x, which cancel out, leaving me with just x e to the x. So the derivative of this result is our original integrand, so this checks out. That is, in fact, our integral. Now, in this example, I just randomly chose what to use for the function u, and then allowed dv to be what was left over in the equation. There's a better way of doing that, obviously, because it only works one way. Like, generally you're going to have two functions that are multiplied, and if you choose one to be u and the other, just let the other be dv, it might be the way that it works, or it might not be the way that it works. So here's a method of deciding what to pick for u and dv to give you the most likely chance that you've got the right combination. Now, some instructors use the acronym ILATE, some use the acronym LIATE. It doesn't really matter what you use. I think ILATE is preferred just because it's a little bit more memorable than LIATE. Whichever is fine. So the idea is that these functions are ordered, these types of functions are ordered in how complex their derivatives are. So logarithmic functions, let me write that out, so the complexity of derivatives. Okay, so logarithmic functions, when you differentiate those, they go from being a logarithm, which is a complex function, to a rational, which is less complex. And so that's a good thing. That makes the next integral that you'll have to do easier to do, hopefully. Inverse trig, the same sort of thing happens. You go from a transcendental function, and when you integrate it, it generally turns into something that's transcendental or possibly involves a square root. But regardless, it's much less complex than an inverse trig. Algebraic functions reduce in complexity when taking derivatives. Often you're talking about the power rule here, so they reduce in degree by 1 each time you take a derivative. trig functions don't really reduce in complexity. They often just simply stay the same complexity or sometimes even get more complex. So for instance, like the derivative of sine is cosine. The derivative of cosine is negative sine. So when you take derivatives of each of those, they stay the same complexity, basically. But when you differentiate some of your others, they actually get more complex. Exponentials, when you take the derivative of exponentials, you're pretty much guaranteed that it's going to like at least stay in the same complexity. So sometimes if you have to use a chain rule, that might end up invoking like product rule next. So the derivatives can get more complex. So we want to pick something for u that's going to differentiate to something that's less complex. That's the idea. So whether you use Eliate or Iolate, either is fine. Either is fine. Because honestly, the only time it would ever matter is if you had a logarithmic and an inverse trig in the same problem, and I've yet to see any of those in a Calc 2 class, so I wouldn't worry too much about it. Okay, so let's do another example. The integral of x times sine x dx. So the thing is, we need to pick something for u and something for dv. And we just go through this process of, like Eliate, for instance. So I don't have any logarithmic functions, I don't have any inverse trig functions, but I do have an algebraic function. So that's less complex than the trig function. So I should be picking the algebraic function for my u, and then my dv will be what's left over, so sine x dx. All right, now I differentiate u, so that will be du equals dx, and I integrate dv, which will become v equals, and the integral of sine is going to be negative cosine. Okay, so the rule here is, of course, the integral of u dv is going to be u times v minus the integral of v du. So let's see what happens when we take what we've learned here and plug in. So u times v, this would be x times negative cosine x minus the integral of v, so negative cosine x again, du, and du is just dx in this case. All right, so this becomes negative x times the cosine of x. These negatives are going to cancel each other to a positive, and then the integral of cosine is just sine, so this would be sine of x. And finally, r plus c. And then we're all done. So once you get through this step here, where you've integrated this part, which hopefully is a simpler integral, then you end up with something that you're finished. And it all comes down to this portion right here, this du. We want this to be simpler than this function that we started with over here, because if this du is simpler, it generally means that this integral is going to be simpler to perform. So that's kind of the key in how we choose u. If we had chosen u as sine x, and don't write this down, then the derivative of that, du, would have been cosine x. Then we would have dv as x dx, and v as the integral of this, which would be x squared over 2, which is more complex. So when we plug things in, we end up with something that's actually more difficult to integrate. So this is not the way to go. So only one combination of u and dv will work. Let's look at another example. All right, here I have the natural log of x divided by x cubed. All right, so we obviously need to pick values for u and dv. So the parts here that I have, essentially, actually I could just rewrite this as x to the negative third times the natural log of x. And then that ensures that I can see my product that I'm working with here. All right, so in a lot of situations we pick the algebraic piece, but in Liate or iLate, it tells you that the logarithmic is a better choice for you than an algebraic piece. So let's go with that advice. So we'll let u be the natural log of x, and then dv will be x to the negative third dx. The derivative of u will be 1 over x dx, and then the integral of dv would give me v equals the integral of x to the negative third, so we would add 1 to our exponent, so that's to the negative second, and then divide by negative 2, the new exponent, that is. Okay. You know what, maybe I'll just rewrite this as negative 1 over 2x squared to make it a little bit nicer looking. I'm not sure if it makes any difference when I actually integrate. But I now have u, v, du, dv, all these pieces that I need. And the process here is that the integral of u dv is u times v, so as I'll write it, negative 1 over 2x squared natural log of x minus the integral of v du. So this is going to be negative 1 over 2x squared, that's v, and then du is 1 over x dx. Okay, I've got some negatives that will cancel. So negative 1 over 2x squared natural log x. I can simplify all this as plus 1/2. This would be 1 over x cubed, so I'll go ahead and write it as x to the negative third dx. And that is something I can integrate. So 1/2 times, add 1 to my exponent, so x to the negative second over negative 2 plus c. And then the last part is just really kind of polishing up the answer here and finishing everything up. So this is going to be minus because of that negative. So this will become 1/4 when I combine those constants, times 1 over x squared plus c. And it's probably a little bit nicer if I just make that under one fraction. So let's just say 1 over 4x squared. And that's probably just fine in terms of a final answer here.